Good morning, everyone. Today I am going to present our research work titled A Lightweight Hybrid Graph Temporal Model with Differential Evolution for UAV Navigation in Cluttered Environment. This work has carried out by me, Shalini Sahu, along with my co-authors Anita Yadav, Ragraj Singh from HBTU Kanpur and Abhishek Bajpayee from Rajki Engineering College, Kannauj. I have completed this work with the guidance and support of all these authors. Now, second slide is outline. In this presentation, I will cover the introduction, literature review, proposed methodology, research, results and analysis, and conclusion and references. I will explain each part step by step to give a clear understanding of our work. Now, goes to the next slide, which is introduction. Natural diseases such as earthquakes, floods, landslides are increasing due to climatic and geological variations. These events often damage communication infrastructure, which creates challenges in coordination and emergency response. In such situations, UAVs provide a cost-effective and rapidly deployable solution for real-time monitoring and disease assessments. They are widely used in surveillance, mapping, and 3D reconstruction. However, UAV navigation in dynamic environments is still difficult because it requires high computation and stable decision making. Therefore, there is a need for lightweight and efficient path planning methods. Now goes to the next slide, which is problem statement. The main problem in the UAV navigation is that it is highly complex and computationally demanding. Existing methods are slow and sometimes unstable, which makes them unsuitable for real-time applications. Classical methods can't adapt to changing environments, and learning-based methods require high resources. Therefore, we need a lightweight and robust hybrid approach that can provide efficient and stable path planning. Now goes to the next slide, which is literature review. In literature review, classical methods like A star and Discasta provide optimal paths but require complete knowledge of the environment. Sampling and meta-heuristic methods improve exploration but may suffer from randomness and local minima problems. Deep reinforcement learning approaches can learn dynamically but have high training cost and slow convergence. Overall, existing approaches lack efficiency, stability, or adaptability. Hence, there is a research gap for a hybrid model that can combine spatial learning, temporal learning, and optimization. Now goes to the next slide, which is proposed methodology. To solve this problem, we proposed a hybrid framework that combines graph evolution led by long short-term memory and differential evolution. The GCM is used for spatial learning to understand obstacle distribution. The LSTM is used for temporal modeling to learn movement patterns over time. The differential evolution algorithm is used for optimization to generate the best path by minimizing path length, collision risk, and energy cost. This combination helps in generating a smooth, safe, and efficient UAV navigation path. Now goes to the next slide, which is architecture. The architecture of our model consists of three main stages. First, the environment is converted into graph and processing using GCM to extract spatial features. Then features are passed to the LSTM network to capture temporal dependencies. Finally, the differential evolution algorithm optimizes the generated trajectory. This architecture ensures stable, efficient, and real-time UAV navigation. Now goes to the next slide, which is environmental setup. For testing, we created both 2D and 3D environments. In the 2D environments, the start position is shown in red and the goal position in green, obstacles in black, and free spaces in white. In the 3D environment, different scenarios are designed with varying obstacle density and complexity. This setup helps us evaluate the model in realistic navigation conditions. 3D environment result. Next slide is we tested our model on three types of environments. The first environment has sparse obstacle representing moderate complexity. The second environment has dense environment making navigation more difficult. The third environment has irregular obstacles which test the adaptability of the model. The proposed model performs well in all these scenarios. The next slide is trajectory results. The trajectory results show that our model generates smooth and collision-free paths. The UAV successfully reaches the goal position in both simple and complex environments. The paths are efficient and stable, which proves the effectiveness of our approach. The next slide is performance graph. The performance graphs show that our model achieves a high success rate and reduced path length compared to the other methods. The results are stable across different scenarios, which indicates good performance and reliability. The next slide is 2D performance analysis. In 2D performance analysis, we compared our model with Grady A star, ST, D3QN, and proposed methods. The results show that our proposed method achieves the shortest path length and highest reward. This indicates better efficiency and improved decision-making capability. Now, next slide is environment voice results. We also compared our model with other algorithms such as RRT, DQN, AZWO, A star, and Disgasta, and proposed model. The results show that our method provides balanced performance in terms of path length, smoothness, and computational stability. It performs consistently well across all the environments. And next slide is environment 3 performance metrics. In the third environment, which is more complex and irregular, our model still maintains stable performance. It generates efficient path with good smoothness and reasonable computation time, showing its robustness in difficult scenarios. Next slide is success rate comparison. The success rate comparison shows that our model achieves 100% success rate, which is higher than many existing methods. And next is conclusion. The proposed hybrid model improves path efficiency, stability, and smoothness. It outperforms classical and deep learning based approaches and suitable for real-time UAV navigation. And last slide is references, which shows that all papers are cited in a introduction and literature review, which are shown in this slide. Thank you so much.